All right, these notes are going to be for your stapled pieces of paper for section 4.5 and section 4.6. We're going to be graphing the trig functions in section 4.5, sine and cosine only, and then in section 4.6 we'll do the other four. We talked in class and yesterday how the trig functions are created using pasta noodles and how they're measured. So this is a picture of where each is measuring. So as your point goes around the circle, these values will either increase or decrease depending on where your point is. And they'll go below the x-axis or above the x-axis again depending on what quadrant you're in. So the tangent, or all 6 trig functions, can be created using a circle, a point on the circle along with these tangent lines here, and then just simply measuring from certain spots on that circle. Okay? So now what we want to do is be able to take these and graph them on an XY grid. These are the points that we have seen already in the past for both sine and cosine. And so these are the points that we're going to be using to graph each of these. They come directly from your unit circle that we learned a couple weeks ago. Okay? Now, we saw this graph in class today, the sine graph. We talked about having a period of 2 pi and a range of -1 to 1. And when we go to graph this, you would graph the decimal versions of these things, like, for example, square root of 2 over 2 is approximately 0.7. So pi over 4 would graph pi over 4, comma 0.7. Pi over 3 would graph square root of 3 over 2, which is approximately 0.9, and so forth. So these points then would be connected together to give you the graph of sine when you wrapped it all the way around the circle. And so this is what the graph would look like. I'll talk about this more in class, about the periodic properties, and show you this formula in class. For right now, just what it means is that if you have an angle and you go a full revolution around the circle, 2 pi, you're going to end up with the exact same y value because you landed on a coterminal angle. And the sine of coterminal angles is the exact same value. Cosine works the same exact way, and so that's why we have a formula for it as well. Okay? Here's the graph of cosine and what it looks like. Some of the points that are going to be graphed on there. There they are. Okay. I'll pause this for you in class tomorrow and we can look at this. And then a few things about sine and cosine. We actually did these in class already today, so I'm not going to go through this. So if you will, go ahead and fill in this part of your sheet for me. Pause the video and I'm going to continue. All right, so in order to actually graph the sine and cosine, we don't have to graph every single of those angles that I just saw a minute ago that were on the unit circle. You're going to graph some key points. The key points being the x-intercepts. Sine has 3 of them. The relative maximum of sine and the relative minimum. There are 5 key points that you're going to use to graph. And then for cosine, it's the same thing. You'll graph its 2 relative maximums, it's 2 x-intercepts, and it's 1 relative min. These are the points that we're going to use whenever we start to transform them and move them up, down, vertically stretch them, and so forth. Okay? Now, speaking of transformations, these transformations are going to be the exact same ones that we learned in Chapter 1. You will notice that we have the A, that's going to represent my vertical stretch or my vertical compression. You have your C, which is going to represent your moving right or left. You have your D, which is going to make it go up and down. And this B is actually new. We did have B being negative. We never had it be an actual value except for -1. So if B is negative, we'll have a reflection across the y-axis. If A is negative, we'll have a reflection over the x-axis. But now also we are going to have what's called a horizontal stretch or horizontal compression. Okay? So now if you'll fill in your values of A, B, and C, and D that create these different transformations, please. Okay? Pause the video as needed, and I'm going to go ahead and move on. So, in order to create a reflection, just like we learned in Chapter 1, you'll put a negative out in front of the trig function. In order to have a vertical stretch, you will change your A value. But we have a new word called your amplitude. Your A actually also represents your amplitude. If you remember from class today, that was the distance from the middle of the graph to the highest peak or the lowest valley. Okay? So whenever you do a vertical stretch or compression, you will also change the amplitude of the graph. So for the cosine graph, the amplitude is 1, but if you make that 3 cosine of x, you're going to vertically stretch the graph by 3. So you'll notice at 0, it now becomes 0, 3. At this point, it now goes down all the way to -3. So the midpoint of this then, the distance from the midpoint to the highest point, is going to be 3. So that's going to be my amplitude for the new graph. If I have 1/2 cosine of x, this is a vertical compression by 1/2, but it also creates a amplitude change, and so the amplitude will go from 1 to 1/2 instead. Your horizontal stretches and your horizontal compressions are going to come from the value of b. Because you are going to horizontally stretch or compress, you're actually going to change the period of b as well. So the b is going to represent how many cycles of the graph that you will see in a normal 0 to 2 pi revolution. I'll show you what that means in just a moment. Which means your period now is going to become 2 pi over b. And so that will be a period change, which comes from your horizontal stretches or shrinks. So for example, if we have sine of 1/2 x, what that means is from 0 to 2 pi, you will now only see 1/2 of the grid, versus, or 1/2 of the graph versus the full graph. So if I look at, for example, in this first one, from 0 to 2 pi is here to here, and from 0 to 2 pi is from here to here. You'll notice you have a increase, a relative max, and then back down at the bottom you'll have a relative min. But in this same interval from 0 to 2 pi, you'll notice you only see the relative maximum. So what happens, you only see half of the graph on the interval from 0 to 2 pi, which means you have horizontally stretched this. So even though this b in this case is equal to 1/2, you have a horizontal stretch, and it's 2 times longer than the original. So we would call this a horizontal stretch by 2, which means it's going to take another 2 pi units to finish this graph, which means you now have a period of 4 pi. So looking at the math behind that, if we use this formula, we would do 2 pi divided by 1/2. You multiply by the reciprocal to make that 2 pi times 2, and that gives you 4 pi. Here's my next example. If I have y equals sine of 2x, what that means then is you're actually going to see 2 full revolutions of the sine period in that same interval from 0 to 2 pi. So if you look at this first one, you see 1 relative max and 1 relative min from 0 to 2 pi. What this 2 right here means is that you will see twice as many. So you will notice you now have 2 relative max areas, and you will have 2 relative min areas. So what just happened is you cycled through the sine graph twice. Once here from 0 to pi, and once here again from 0 to 2 pi. I meant to say pi to 2 pi. So you have 2 full graphs here. So what that means is you actually have compressed this graph horizontally. You have a horizontal compression. It is 1/2 the size that it used to be, because it's only going from 0 to pi now instead of 0 to 2 pi. So it is 1/2 the graph that it used to be. And so to use this formula to come up with the period then, you would do 2 pi over 2. And so 2 pi over 2 means I would have a period of pi, which we can see from the graph. As it cycles through one full wave, it did take only pi units to do that. So that makes sense. So now, this example 1, we're going to use the same work that we did in Algebra 2 to create our transformations and graphs. So the first thing we're going to do is we are going to figure out what those transformations in this case would be. So if you want, please go ahead and pause the video and write down the transformations first. This, as we learned in the past, creates a vertical compression by 1/4. This negative is going to reflect it over the x-axis. And we just learned about this. So what this means is that sine is going to cycle through 2 times in the normal 0 to 2 pi period. Because it's going to cycle 2 times, it's going to be half the length that it was before. So this is going to be a horizontal compression by 1/2. So the way that you can remember it is that if b is bigger than 1, you have a horizontal compression by 1 over b. Alright, so now let's take that information. After we had our transformations, we would write a XY coordinate grid or we would write an XY table for our values, and we're going to do this based on sine. Please remember, we're only going to do the ones that are the key points. So those were your 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if I go through those points, the sine of 0 is 0, the sine of pi over 2 is 1, the sine of pi over is 0, the sine of 3 pi over 2 is -1, and the sine of 2 pi is 0. So these will be my 5 key points that I'll use to transform. Just like in Algebra 2, we will take these transformations and we will apply them to vertically compress by 1/4. We'll take y and multiply it by 4. To reflect over x, we'll take y and we'll make it negative. And to horizontally compress, make it smaller, we are going to make half of my x's for my original points. So all I have to do now is take these values and run them through these formulas and then graph it. So 1/2 times 0 is 0, 1/2 times pi over 2 is pi over 4, 1/2 times pi is pi over 2, we have 3 pi over 4, and pi. And then you'll do the same thing with your y's. So we'll have 0, -1/4, 0, oh, I lie, it's +1/4. Oh yeah, it is -1/4. +1/4, and then 0. You would simply take these points and you would graph them on the grid that I've given you. So 0, 0, pi over 2, 0, pi, 0, and then pi over 4, you would make, that would be -1.25, or -0.25, so you put a dot there. And 3 pi over 4 is between pi over 2 and pi, so you'll put a dot at 0.25. So you'll create this graph by connecting your dots. And then I do expect you to use this same pattern to finish off the rest of this all the way to -pi. So you'd have another point at -pi over 2 as an x-intercept and -pi. You would have a relative max now and at -pi over 4, 0.25. And you'd have a relative min at 3 pi over 4, -1/4. And so this is what your graph would look like. Okay? So now for phase shift, this is going to be your horizontal translations left or right. So in this case, your phase shift would be the C over B if you don't go ahead and factor your B out. If you do go ahead and factor your B out, however, like we were taught to factor out the negative, it's the same idea. If you factor your B out, this would become X minus C would have to be divided by B in order to figure out the move left or right. And so you actually end up with the same exact value for your phase shift, which in this case is C over B. So if the B has already been distributed, you can use C over B for your phase shift. If it hasn't already been distributed, if you go ahead and take the B out yourself, then you get the same exact value as your phase shift, your C over B. So the vocabulary for this one is phase shift, and it represents the number of units you go right or left from the original part of the graph. In this case, we have y is equal to sine of x minus 4. In this case, if we use that formula, C is pi over 4, B is 1. So if we do pi over 4 over 1, our phase shift would be pi over 4. Which, horizontally, this means that I'm going to shift right pi over 4 units. So if the blue graph is my original graph, I would take all of my points and I would move them pi over 4 units. I would leave the y values alone and simply take the x values and add pi over 4 to them. And the red graph would be your shifted graph. And so now I'm going to start a new video to do the rest of these examples.